AI is a big buzzword for a lot of cool technologies. Today, we want to peek behind the veil and look upon the implementation and details of a piece of AI. Welcome to Data Model for an Open Search AI framework. I'm Maximilian Werk from Jina AI. So first I want to introduce Jina, what it is, and some basic concepts. Then I want to talk about the data structure and the flow that Jina uses mostly. Then we'll go through an example and have some conclusions at the end. So what is search? Search is not just Google or Bing, but searches happen on almost every major website that you see in the internet. You see it on Twitter, LinkedIn, Stack Overflow. They research for information that you want to get. Or you search on shopping sites like Amazon or Zalando. And what you search behind is always different. Sometimes it's articles, sometimes it's a piece of information, a person, some tweet. So there are a lot of different use cases for search and the different ways to search. So what is a search framework? A search framework is a piece of technology which allows you to take your data and make it searchable. This is not just a database like traditional MySQL or PostgreSQL, where you structure your data and then you write very specific searches in SQL, but this is more. It is something which allows you to also do pre-processing, post-processing of your data and get the needle in the haystack. One example for traditional search frameworks is Elasticsearch. There you usually have string matches and do everything on strings. What it also allows you is some pre-processing, so you can do lemmatization and other things with the text that comes in. But the traditional search frameworks have the big disadvantage that they usually only work on strings. So what is Jina? Jina is a new state-of-the-art design pattern for search workflows. Design pattern means it is not only some tool that you use, but you can also learn the language of Jina and then use this language to design your search workflow. And it lets you leverage the latest deep learning models right out of the box. And you can deploy wherever you want. So it is universal, in the meaning you can not only search text, but also images, videos, and whenever you find a deep learning model or some model that helps you, that can leverage this piece of information and make it use this piece of information, then you can search for it. It is easy to use, so we have examples that introduces how you can use it, and you don't even need to write Python. Ideally, you only have to write YAML files. It's cloud native. Currently, we support AWS, and we also go soon for Google Cloud and Azure. In principle, it is also cloud agnostic because you can Dockerize it and then deploy wherever you want. It is scalable. You can shard and use replicas for get more instances and get more power and more speed. It is extensible. You can bring your own algorithm, your own piece of software that you want to introduce into your search workflow and just plug it in. It uses state-of-the-art NLP or other models. So whatever deep learning model you can find, you can plug it in. And currently we support the latest Torch and PyTorch and TensorFlow models that are there, like BERT. It is completely open source, so you can contribute it, you can use it, you can look into the code, you can understand how it works, and you can just use it freely. And it's community driven. We have already quite a community and a lot of people that help us implement it, and we have more and more users. We can search, as I said before, text, images, sound, video, and also between these things. What does it mean between these things? So if you search for orange, you might get back pictures of oranges. This is from text to images. And somehow to demonstrate how video works, when you have a GIF search and you search on the left-hand side for a GIF, like this, you get other faces back. When you search for a face, and you get like other football fields back when you search for a football field. So what does AI search now mean? It's a big buzzword, but what does it mean? In the end, it means embeddings are everywhere. So let's have a look at the example. You want to search for lyrics, and let's think about the title "What's Up" with the text below, and then in the end you want to search with what is up and want to still get the text, the lyric back. So what happens is, first of all, we create embeddings, and that means numbers, vectors. So for each piece of information that we have, we create these vectors. You can think about the title, what's up, becomes this vector, which is just a 100, 150, 200 dimensional vector with floats in it. And the text becomes another vector, which is a different one. And in the end, this is just a huge vector space. And now our query also becomes a vector. And searching for this now means that we want, when we get this vector, want to find close vectors that are really close to this vector. And the one with the shortest distance, they match. And this means searching means getting shortest distance matches in a big vector space. And how do you get these vectors? Well, this is named embed things or encode things. And for this, you use deep learning models. For text, for example, BERT, one of the different BERT models that are pre-trained, or you can train your own model to generate these embeddings. And embeddings for us are first-class citizen, while for traditional search frameworks, strings and numbers are first-class citizens. For us, it's vectors. And these are the things that we use to find our results. Now I want to introduce our data structure and the concept of a flow. The data for us is usually information in a tree. So whenever we have in our algorithm some piece of data, some data that we give forward, it's always organized in a tree. In this tree we have some root node, and then we have children nodes, which might be pieces of this big information or matches of this information. And then they can also have child nodes again and again child nodes. And then I already named flow, and flow is somehow how the data flows through our system, and then we define the single steps that happen. So let's take an example. We have again a lyric, and first we want to segment the lyric. So the lyric comes in, we segment it into a single piece of information, then we encode it, get the embeddings out of this for the pieces of information like the title and the rest. Afterwards, we index it, write it to some database, and then we also, for the full piece of information, write it to a database. These flows can be described in YAML format, like shown on the left-hand side, where you somehow define, okay, I first want to have my segmenter, then I want to have an encoder, which follows the segmenter, then I want to get my chunk indexer, which also follows the segmenter, and I want the document indexer, which follows just the gateway, so some virtual step at the very beginning, and in the end I want to join the other two. And now we could imagine, okay, how does this encode look like? Well, you say, I want to use the transformer torch encoder and want to use this model. And that's how we use this model. Nothing more needed. And you can define flows either via YAML, via Python, or even on our dashboard, you can drag and drop them together. Okay, now we have a flow and we know somehow this and that happens. But now how do we merge this with data? So think about the full lyric comes in. In the beginning, we just have our root data node, which is the full lyric. Then we segment it, for example, into the title and each sentence might be. Afterwards, we encode these sentences, which are now child nodes, and now they become numbers. Because encoding just means get encodings, so numbers. Then we go to the chunk indexer, nothing happens to the data, it just writes the data away, and that's it. Now we saw these different building blocks. For example, we saw an encoder, which we can use to get the embeddings out of the raw information. We support, for example, the transformer torch encoder or Flare text encoder, if anyone have already heard from Flare. We also have segmenter, which splits, for example, down our input data. We have synthesizer, but we have also segmenter like PDF extractor, where afterwards you get the text and the images of a PDF. Or you could think of things like a sliding window segmenter, when you have lyrics and you always want to index three lyric in a row somehow. Or if you have sentences in a text, you always want to index 3 sentences in a row because you want to search somehow for semantic meanings. There you have different ways of segmenting things. We also have the same for images and videos. Then we have indexer, which in the end are our databases. Currently we have a NumPy indexer, but we also support the NO indexer. And finally, when you want to search for things, we have different rankers. You could think of traditional TF-IDF ranker or like Levenstein ranker in the NLP domain, which just ranks depending on the edit distance. And all of them are called executors. The executors somehow are the things that do something. So each of the blocks you saw before in the flow is one executor. So we want to be a generic framework. That means we want to be able to create embeddings on multiple levels. If you think of a big text, it could be the full text, which just get one embedding. But you could also do the embeddings on paragraph level, sentence level, or word level, depending how detailed information you want to search for. And we also want to enable, with our data and flow concept, to search across levels. For example, for image search, you might want to give in a piece of an image of a dog, but in the resulting image, you just don't want to get the dog back, but a whole picture with all the surroundings of the dog, not just the dog in another picture, which would be searching from a small chunk of information, the image of one dog, to a whole picture where dogs are in there. And we have some requirements for our data model. We want the data model to be flexible. So it should be, should be able to handle different types of data. It should have simple rules. It should still be powerful to serve a lot of use cases. And it should be MIME type agnostic. So images, text, videos, all should be able to put into the data model. And ideally, it should be easy to use, and especially in combination with the flow. So I already showed you the tree. Now we have 3 different types of nodes in this tree that we use for our data model. We have the red root node, which for example can be a full lyric. And then we have chunks, which are somehow pieces of the of the upper node, of the parent node. And the chunks could be title, sentence 1, sentence 2. Another example, when you have a PDF, the chunks could be image 1, then a piece of a text, and then another image, and perhaps more text and more images. But we have a second type of child nodes, which is matches. So when you search for what was love, you might get matches back, which might be what is love, what was groove, or who was loved. And after searching and going through our index, we might get back these matches in our data structure. So these are the type of nodes that we have in our graph. And now a graph looks nice and you have a nice mental model, but what means a graph in code when we go to really coding things? In the end, it's super easy. When you think of the root node, it's just root, just a variable called root. In Python, when you say then, okay, please give me the chunks, you get all the children which are chunks on a lower level. And you say, okay, please give me the last chunk with the chunks of -1, and then the chunks of all of these, and these are again all the child nodes. So whenever you have some more objects and lists that are somehow have sublists, you can also picture the same thing in your head as a graph. And now we already see, okay, we said, okay, all chunks are somehow put together in one family. When we go now and name these families, we can have a root node. And this root node just has 2 types of subfamilies, either the chunks of it or the matches of it. And each of these things can again have either the chunks as childs or the matches. And here again, these matches of matches can again have either chunks or matches. So whenever you got a root object, just by giving a string, which is either a single R or a combination of C and M's, you can define on which family you want to perform some tasks. So imagine you have the root family, which is a full text. Then here you have the paragraphs, and here you have the sentences. And you only want to encode the sentences. You just have to say, please encode sentences on the CC level. And then the encoder does not perform on the C level or on the R level, but only on the CC level. since encoding is quite expensive, it might be important that you just don't encode everything. And now I want to go through an example where I demonstrate somehow how this concept of this data works together with the flow. So again, let's imagine we want to index some lyrics. And we want to search for some lyrics. We have the search. Someone searched with "what was love" and "hurt me." The first thing is we want to sentence this and want to sententize on the root node. So whatever is in there should be sentencized. And what happens? We create two chunks. One chunk is "what was love" and one is "hurt me." The reason for this is since we search on the sentence level in lyrics, we want to somehow, we need to also split the query into sentences. After this, we want to encode them because we know, okay, whenever we want to search, we need embeddings. So we say, please use the transformer torch encoder and use it on a level of C, so on the chunk level. And now the chunks got encodings. In the next step, we want to find matches for these chunks. So we say, okay, we want to use the NumPy indexer, our database, and please do this also on the C level. So search on this level. And after we searched on this level, we get for each of the chunks matches back that are now here on the lowest level. Okay, these matches now only have some numbers, so we perhaps want to get more information what is in there. So we say, okay, please also use another indexer, which is an indexer with, like a key value lookup, where we can get for each of these matches the real text that's in there. We don't put the real text to the same database as the embeddings, since that might makes it slower to run. And for speed reasons, we want to put the embeddings in the one database without any meta information. Okay, but now we have the meta information for display reasons, for example. But still, we want to get full lyrics and not just single sentences. So in the next step, we somehow need to get out of these lyrics or out of these single sentences the full lyrics. And for this we say, okay, please go on the chunk level. This is now a little bit unintuitive, but please go on the chunk level, and the matches of these chunk level propagate up to the root level. Now this is what happens. We get on the root level now matches. They still have an ID. So finally we have to again with this key value lookup check, okay, what are the meta information of the full text. And this we do just on the match level, so just on this level. And you see how we, with defining our families, can always say whatever piece of encoder or with the executor we have, might it be an indexer or an encoder, we can always say where on the data structure should you apply it. And that's it. Let's have a short look on a demo how it looks. So let's check back to our requirements. We wanted it to be flexible. Well, yes, we can go on every level of complexity on any chunk level, so that's possible. It has simple rules. You somehow just have to define on which level of information you want to apply things. It is powerful. We still can do all the chunking, we can use it together with all the different executors that we can think of. Whatever you put into the nodes, you can put whatever data you want, so they're also MIME type agnostic. And from my point of view, they're also kind of easy to use. So we had a different data model before, which was much more complicated, and now once you played around a little bit with it, it's quite straightforward how to use it. So, done. Now let's get to the final summary and have some conclusions. So from technical side, our data is structured as a graph. So whatever you know about graphs, you can more or less apply to the data. Our executors can be applied to any part of this graph. So you can, whenever you have some data floating around, you can say, okay, please only do something on this piece of my current data structure. We can use it for all modalities. And when you bring your data, it's kind of easy to use on your data. We have a lot of examples in our example repository, so go ahead and play with it. It is fun. And from a somewhat more business point of view, we got our first adopters. There is a legal search from Arthur Tan, which is really cool. So I can only recommend have a look into it. He somehow has a search for legal texts, and it works pretty cool with Jina. And coming out of our hackathon in September, there is a story chatbot with Jina and Rasa, and this is also pretty cool. Just search Google for it and you will get the link. I haven't pasted the link here because it's quite big, but Google for it, it's a pretty cool thing. So whenever you bring your data and have your problem, with Jina you can plug in the best model to solve your problem. Because it might not always be the same model that solves your problem. If you want to learn more, you can find us on GitHub. You can try out our hello.jina.ai, which is our onboarding example. You can join us on Slack and ask questions, join the community, and you can follow us on Twitter. Thanks a lot for your attention.